To begin to understand Earth's climate, we need to understand Earth's energy balance. Now, the sun is the source of the energy available to drive Earth's climate system, and so we should start with understanding the sun's energy balance. Now, one of the most important things to understand about the sun is that the sun is relatively hot. And the type of radiation that a black body, a generic body, is going to radiate is going to depend on its temperature. The sun is somewhere on the order of 5,000 to 6,000 degrees Celsius at its surface. And if you take a look at what you expect from first principles to be the types of radiation that's emitted from something that's 5,000 degrees Celsius, it matches pretty well with what we see as far as radiation coming out of the sun. And that radiation is divided up into different wavelengths. So there's relatively short wavelength, intermediate, and long wavelength energy that comes off of the sun. Some of this is in the UV, the ultraviolet range, relatively short wavelengths. Most of this is in the visible end of the spectrum, and then the infrared portion of the spectrum, you'll also find radiation from the sun. Now, the radiation at sea level, if we measure that, is a lot different than what is found at the top of the atmosphere. And that's because there's absorption of some of that radiation by different gases that are present in the atmosphere. If we partition all the energy that's coming out of the sun, somewhere on the order of 8% is in the ultraviolet range, 39% is in the visible range, and the near infrared somewhere on the order of just a little bit over half. So a large proportion of that energy is in wavelengths that we can see, and more than half are on longer wavelengths. Now, just as I showed, when we compared the sunlight, the radiation distribution at the top of the atmosphere and at sea level, that there are gases and there are particles in the atmosphere that absorb sunlight. And each gas has its own unique absorptivity. So here we have methane, for example, and that's a gas that you can find in the atmosphere, and it's got its own unique set of peaks of absorptions. N2O, for example, has a different set of peaks that are slightly offset from methane. Oxygen and ozone, much further out here. CO2, you can see very strong peaks here and definitely on for long wave radiation. Water is also something that absorbs radiation in different areas. When you add all of these up together, this is what the absorption peaks look like for the atmosphere as a whole. And you can see a lot of the long wave radiation, here the wavelengths are shown in micrometers instead of nanometers like before, that a lot of that long wave radiation is absorbed. And there's windows where radiation is not going to be absorbed by the atmosphere. Once sunlight is absorbed, it's not radiated as light. It's radiated as heat. And because the Earth is cooler than the sun, it's radiated at longer wavelengths typically. So here's figure 2.2. And this shows, again, here are the wavelengths. This is going to be in micrometers. That's the incoming solar radiation, really tightly compressed in UV, visible, and near infrared. And you can see terrestrial outgoing radiation is in these much longer wavelengths, much less energy involved in each of those. So now the question is, how is energy partitioned? We know that energy comes in to the Earth. So if we have our surface, we're going to have energy coming in from the sun, and then it's going to get partitioned in different ways. Some of it's going to get absorbed in the atmosphere. Some of that might get reflected, for example. Others, it's going to be absorbed and then re-radiated. And the partitioning of energy is really critical to thinking about the temperature of a site, as well as consequences for energy flow through ecosystems. So this is diagram 2.3, which is very complicated. There's a lot of arrows here going in a lot of different ways. We're going to focus in on the shortwave incoming radiation first. So here, for example, is space, and here's the incoming radiation. 100%, we're going to work on off of that number and take a look at partitioning. And you can see that there's different arrows here that represent the major partitioning of energy. So on average, about 30% of the incoming shortwave radiation is reflected back to space. And you can see it's reflected in a couple of different ways. So the air actually itself can backscatter, can reflect some of that light. Clouds also are highly reflective, so some of that energy that comes in is reflected just back out into space just because it hits clouds, and some of that is reflected by the surface. And in total, 30% on average is reflected back out into space. And if it's reflected, it's going to be in relatively short wavelengths. Once we do that, somewhere on the order of 23% of the incoming shortwave radiation is absorbed by the atmosphere. So you can see here that H2O, dust, ozone is going to absorb about 19%, and then clouds, water vapor, that's going to absorb somewhere on the order of 4%. And that's about a quarter of all the incoming energy is absorbed by the atmosphere, it's absorbed by clouds. So 30% is reflected, 23% is absorbed by the atmosphere, some component of the atmosphere, and that leaves us with 47% left. Absorption of direct solar radiation, that's 22%. Absorption of diffuse sky and cloud radiation is 25%. So what happens is that as that energy comes in, it's all direct. And then later, sometimes it's scattered a little bit, and then it becomes diffuse, and it starts going in all different directions. So we think about partitioning of energy into direct versus diffuse radiation. Now, albedo is important, and it's an important term. The reflection that we talked about, we can quantify. So what percentage of the energy coming in, of the light coming in, then is reflected away? And that number is albedo. And if we talk about having a high albedo, something's very reflective. If it's a relatively low albedo, it's not reflective at all and absorbs a lot of that energy. So now, having gone through the patterns of understanding the partitioning of shortwave radiation among atmospheric components, clouds, and the terrestrial surface, it's important to understand that the shortwave radiation that's not reflected, that's absorbed by these different components, eventually has to be emitted as long-wave radiation, lower energy wavelengths. So this long-wave radiation, you can see numerically that 30 and 70 is equal to 100, and essentially what this represents is that for all intents and purposes, all of the energy that comes in as shortwave radiation is eventually emitted either as shortwave or long-wave radiation. And the partitioning of this, the numbers we don't necessarily care about right here, but it's important to understand that almost all the energy that is absorbed by the atmospheric components such as water, CO2, or ozone, is emitted to space as long-wave radiation. And all of the energy that's emitted by clouds is either, or absorbed by clouds, is either emitted to space or downwards into the terrestrial surface. In the same sense that all of this terrestrial, all the energy that the terrestrial surface had absorbed was also emitted upwards. And there is an important thing to think about, in that the atmosphere and the clouds are often heated from below, so that the surface itself absorbing energy, releasing it as long-wave radiation, is another source of heating of clouds as well as the atmospheric components too. So these are not just heated from above, but also from below. And next, what we're going to talk about is sensible and latent heat flux, and this is really the most important components of the energetic balance of the terrestrial surface, and we'll get into that next. So as you think about this section, what's important to understand is really thinking about the partitioning of the shortwave radiation and understanding how much of the incoming shortwave radiation is absorbed by atmospheric components, is absorbed by clouds, or then terrestrial surface, as well as being reflected away by each of those different components. In addition, think about long-wave radiation and understanding the pattern of heating that occurs with it. How much of that energy that's absorbed by those different components is radiated upwards versus downwards, either being lost to space or going down to heat up different components. And in the next section, we'll really think about how much heating of the Earth there is by those different components. And knowing what the patterns of long-wave radiation are help to a certain degree, but we have to really think about it a little bit differently to understand how the Earth gets warm and why it's the temperature that it is, and for different ecosystems, why they heat up differentially.